Welcome to the Rootkit lecture. My name is Owen Redwood, and this lecture is part of the Offensive Computer Security OpenCourseWare hosted at hackallthethings.com. So rootkits are essentially code, not necessarily malicious, running at either root or kernel privileges that has been injected into the process space or the kernel space. And all sorts of parties build them, ranging from marketing to MMO developers to publishers who want to enforce digital rights management to also law enforcement backdoors. Then there's government level espionage to industrial corporate espionage and then political espionage, finally cybercrime purposes. There was a time that MMO developers were, namely Sony, developing rootkits for anti-cheat detection. Um, and this shocked a lot of the customers as after people reverse engineered it, they found a number of vulnerabilities and weaknesses inside the rootkit design that in theory exposed all of their customers to essentially attackers that could exploit this and then have an instant rootkit on the target system, which is something they probably should have been held liable for, but I digress. We're first going to cover Linux rootkits and go into the difference between kernel land and user land rootkits. Then after that, we're going to go into Windows land. So here are the ways to deploy in kernel land a rootkit that we're going to cover. Loadable kernel modules, which is the official sanctioned way of doing kernel development. Hooking, decom, kernel object hooking, runtime patching, and then we're going to cover a user land rootkit with the source code for Azazel. So loadable kernel modules, also known as LKMs, are synonymous with kernel loadable objects, or KLDs. We're just going to call them LKMs for the remainder of this course. They are typically .ko files that contain binary code that is meant to extend kernel. So it's designed specifically for operation in kernel space. So there's a key difference between code that's meant to run in user land and kernel land is that kernel land does not have functionality sometimes to do specific functions like generate random numbers, because it doesn't have the libraries universally shared throughout the different modules and aspects of the kernel, deal with floats and large numbers, and etc. It really behooves one, if they're reverse engineering a rootkit or considering developing one for research purposes, to dive into an operating system design course, as that is probably the best way to get started in that arena. Anyways, if one does this, they'll quickly find that this is the official way of advertised for modifying the kernel. This is how all drivers are done, and you will find examples of kernel modules in /lib/modules. And as a note, you can disable all kernel modules in the flag set at procsys kernel modules _ disabled, but your system stability will most likely suffer, if not just cause a kernel panic and crash. Now, for a malicious loadable kernel module, one would have the capability of intercepting almost any standard function that the kernel might be handling, whether that's keyboard input, packets incoming or going out on the wire, as well as any other hardware that would include webcams, microphones, and etc. So obviously this would enable all sorts of keylogging, backdoors, and etc. for an attackers. However, the ways of inserting or loading a LKM are not stealthy. ModProbe and LSMod, if I recall correctly, leave a lot of logs in the system that one would have to clean up, but it's very easy to pipe those logs to a remote system where an attacker would not have permission or access to overwrite them, which would be the correct way to do these things in a distributed network. At least that's the way I would do the system administration. Now that brings us to the next technique, which is hooking. This is a technique primarily originating in the software development and debugging side of computer science. It involves employing a kind of a handler function, not like an exception handler, but a function that is called before the target function runs to handle some sort of debugging. So how this would be inserted is that at the jump destination into the function, there would be, at the very first line of code, would be some jump to the handler, the hook. The hook would run, and then the hook could return back to that next line of code and resume the functionality of the original intended function. This is typically the way it's done in debugging. However, now, if this is used in a malicious manner, the attacker need not return back to the original functionality. They can re-implement 100% of it and have special cases that are in place to handle evading antivirus, evading system administration checks, evading rootkit checking, hooking detection, and all sorts of other white hat techniques that would be used to detect a rootkit using this technique. Now, there are a wide number of ways to hook things other than the aforementioned example, and we're going to dive into this more when we get into the Windows section of this lecture. So, system calls, to wrap this part up, are a typical target for hooking, and it enables easy keylogging and backdoors. Now, directly manipulating the objects used by the kernel in kernel space is another legitimate way to inject a rootkit. And all operating systems use some sort of objects to do record keeping within their main memory. And these structures can be directly manipulated without an existing LKM or doing any form of hooking. Hell, you can hide an entire process in the /proc structure or the all-proc list, which is more sneaky. The proc structure is technically not part of the file system. It's all a virtual directory. But hiding it directly in the all-proc list is a more sneaky way to do it. You can hide open ports if you edit the right table that contains that information, and so on. The problem with this technique is that an attacker will, I guarantee, will face synchronization issues at the point of injecting the rootkit with this technique. If you can't lock the object, edit it, finish off the rootkit injection, then unlock it, the kernel may preempt you before it is finished. And if that happens, it won't be a simple seg fault, it'll be a kernel panic and full crash, which is much more noisy and messy. And so there's a number of countermeasures. The one I like is a Linux kernel integrity measurer, and that is, you can read about it here. It's essentially a top-down approach for enumerating all of the major objects, tables, and etc. that are used in the kernel, whether it's individual drivers and etc., and mapping out what those tables should look like. That's assuming there's no randomization in the kernel and these things are static. And then going through periodic times and ensuring that the integrity of these objects is still intact, and raising flags if it is not. Unfortunately, this is complicated by randomization issues, most notably kernel ASLR, which we will touch on ASLR in a later point in this class during the exploit development lectures. But kernel ASLR is effectively useless at mitigating kernel exploitation because of how many, let me say, information leaks and address disclosure vulnerabilities there are just strewn throughout the kernel and all of its drivers. So it doesn't stop. KSLR does not stop this style of rootkit injection, but it does stop this style of rootkit prevention countermeasure, which is sad. It's more ineffective than effective. But that's my opinion, and I digress. So, objects can also be hooked instead of just directly manipulated, and this relies on objects that have pointers to other things or where the other table exists, and that's where the hook would exist. And so, for example, if you wanted to install a keylogger, you could simply hook the device entry in the device table, and when a function calls that to say get characters or get this or that or get key press, it will jump to your hook and boom. Lastly, instead of hooking things by getting the handle for the objects or looking them up by their VMA, you can always iterate through the kernel memory virtual device, which is at dev kmem. Look for the, I guess, signature for the target object or target memory and simply patch it in. Now, you can also patch in instructions, not just objects. You can look for the .text segment and other binary segments that involve the kernel logic and patch them yourself. And this is a bit more risky. So here's an example algorithm. Say we wanted to use this technique to patch one of the system calls to do something malicious instead. Let's target the makedir, which is make new directory system call. The first thing you should do is, for however long your payload is, let's say our payload is just kmalloc for this instance. Say it's 50 bytes. Save the first 50 bytes of your target system call as aside, just in temporary space. Overwrite the first 50 bytes or the size of your payload in that system call's target space. This may cause us a kernel panic doing this, however. Then, the next time that function is called, makedir, it will run your malicious code. And if you're interested in doing this only in a time-based manner to, say, evade antivirus, rootkit checks, and etc., you would then restore makedir with the original temporary chunk you saved aside in that temp space. And that's simply all there is to it. Now that brings us to userland rootkits. We're going to, for the rest of this part, go over the Zazzle rootkit, which is a userland rootkit that works by LD preload injection. LD preload is a kind of historical technique that has caused a lot of problems. There are kernel patches, grsec and patch, that lock down and prevent this technique from working. But essentially, if a user has the even ability to edit certain files in the /etc directory, they'll be able to pull off a LD preload attack that enables the preloading of essentially every process that runs with a perhaps malicious shared object. And finally, at the end, for the sake of detection and countermeasures, there's a blog post listed here. So let's dive into the GitHub. And this is the Zazzle.c main function. Oops, that's the dev page. Here is all the code that's put into the rootkit. Again, this is open source for the sake of research. It delves into what techniques attackers may be using for anti-debugging, anti-detection, and etc. There's documentation, and let's dive into Azazel.c. So again, this assumes this will launch once the LD preload attack succeeds, and we'll look at some documentation on that. But first, we're going to look at the init function. So the meat of it is here in the init function. Essentially, they have this syscall table which they've mapped out in the constants, which is here. There's about 24 entries, and each one is escaped hex of varying sizes. And what they do is they build a character reference, syscall. They XOR it with this mask, which is defined here by XORing each byte with FE in hex. And then go through and populate this syscall list with a reference, a symbolic reference to the dynamic loader, and they just iterate through it. Pretty simple. And then that saves that syscall table. It's not really a hook. It's kind of an indirect way of accessing everything. It's nice and neat. And then for the rest of the functions that they want to instead of hook replace, because they're doing LD preload, they define them here. So let's find some good ones. Access fopen, as in file open. fopen 64-bit. lstat 64, open, remove directory, stat 64, etc. Unlink. So the debugger states that it's hooked once this is called, and technically that's true. And it obviously has conditionals for what it's going to do. It sets cases for whether or not it is the rootkit owner doing this, then it just calls the legit system call, or if it is an invisible path that shouldn't be revealed to the victim, and then it calls the respective saved system call, which is neat. And does this for all of them. Obviously, it can be edited to have multiple different cases and to allow other things. I think there's a hook for except in here, which sets up a shell if the if the socket accepts the right call, which requires creds and etc. But it's a neat little rootkit that you should, if you're interested, look at. And it's Choke Points Azazel rootkit on GitHub. Let's get back to the lecture. So again, they have a blog post on how to detect such a technique, and it's a really cool, interesting research project. So another source you could look at for Linux rootkits is Designing BSD Rootkits. It's a good short read with great technical examples. Now that brings us to Windows rootkits, and there's a really good book, The Rootkit Arsenal, which is 700 pages, almost 800 pages I've got here. Fantastic reference manual on rootkit design, development, reverse engineering, and debugging and detection in Windows land. It's as recent as 2013. Kernel mode drivers for Windows are analogous to Linux's loadable kernel modules. They're both the official channel to insert executable code into kernel space, mainly for drivers or shared objects of the sort, maybe firmware, who knows. And it allows access essentially to the hardware. Now, the way a user application would make a request to
access a kernel mode driver's function, say it exports an API and it's trying to do something very specific and gain access to hardware, is that it would go through NTDLL. The NTDLL for that respective function would call sysenter. That would jump into kernel space, and KI fast call entry would handle the request, which would pass along to the respective NT class of system calls. They all begin with capital NT. And now, since it's relevant to kernel mode drivers, the IO manager subsystem will kick in, and so IO class function will be called by a system call, and that will result in IRP packets, IO request packets being sent to the kernel mode driver, kind of a form of like inter-process communication, but not really within the kernel. And the kernel mode driver itself may interact with the hardware, typically through the hardware abstraction layer, which is a DLL provided in kernel space. And those functions begin with HAL prefix, and that will in turn interact finally with the hardware. And the reason for all of these layers is kind of to shield the kernel and operating system from userland developer mistakes, and also to have partitioning within the operating system, albeit from my studies, kind of convoluted partitioning that has a lot of redundancies and overlap, but I digress. So, developing a kernel mode driver does not take a lot of code. In the Rootkit arsenal, most of the examples are about one page of code, and it allows a lot of capabilities at that level, since it's so low level in the operating system. And the problem with this approach is that it is very detectable, and it is not stealthy at all. A common countermeasure in Windows to the abuse of the official channel for inserting kernel code, aka kernel mode drivers, is kernel mode code signing. And I'm a big fan of code signing techniques. Typically, they work very well. And when 64-bit Windows came out, they required all KMDs to be digitally signed, so they pushed out a lot of software publishing certificates to the vendors and driver developers that Windows primarily worked with, and it wasn't applicable, however, to 32-bit versions. I think now it's not a big problem. All versions of Windows do it, and at least at the 32-bit level, they require all the core binaries, or at least a subset of them, to be signed. So how this works is that the kernel mode driver will have a signature either in the binary or in the same directory pertaining to the binary itself, and before it is loaded, the kernel will do a hash of it or do some form of digest of the KMD, correlate it to the signatures hash, and if it checks out, then the signature would and the cryptographic checks on the signature and the certificate check out, then it would be loaded. And in order for an attacker to abuse this, they essentially would have to get themselves a valid software publishing certificate, which, unfortunately for us defenders, is too easy for attackers. I believe in 2012 or 2011, there were two independent teams of researchers that wanted to investigate how easy it is to get a code signing certificate from Microsoft for arbitrary driver level work. And they simply just formed an LLC, submitted a request, and they got one. And they were able to do malicious development thereafter, and nothing would stop a Windows operating system from loading those malicious KMDs. So they released their research at a conference talk. Maybe it was DEF CON, I don't know. And Microsoft responded by revoking the certificate. Maybe they've tightened their policies for getting a certificate, but theoretically it is possible for developers to get such a code signing cert. They could do it alternatively by getting a job at a valid vendor that has such a certificate and then leaking it or using it themselves maliciously, in a sense, insider threat. And then they can always piggyback on signed valid drivers, um, which I'll get back to in a little bit. So this slide is redundant because I already talked to it all. So the way to piggyback on existing kernel mode drivers is by kernel mode driver exploits. Finding vulnerabilities in one of the hundreds of drivers used by the Windows kernel. Most of them are by third parties, and it is very, very common for them to have vulnerabilities. And there's nothing Microsoft does or can do about these vulnerabilities and developing an exploit for them. The payload for the exploit is essentially another kernel mode driver, and by deploying it in this route, it leaves no logs. It's highly stealthy and also offers high capabilities. High complexity here on the slide is in terms of capabilities. You're allowed a lot of complex capabilities at this level. And this is not uncommon. Another technique is modifying or hooking the system call tables, just like Linux. So for Windows, there are multiple call tables that could be targeted with this approach. The import address table is such a target for user space on a per process basis. There is in kernel space the IDT, which is the interrupt descriptor table for handling interrupts. The CPU MSRs, which are model specific registers. They are configuration registers that are only used by the operating system. Applications should never end up using them. The contents of the MSR define how the CPU behave under different models, and typically there's a RD MSR, a WR MSR, a read MSR, and a write MSR respectively. Instruction that are used for interacting with the MSRs and writing and reading them. Then there's famously the global descriptor table, which defines the characteristics of various memory segments. For each memory segment, it's going to be dictating the base address, the size of each segment, the access privileges like executability and writability. The GDT will also hold other objects sometimes as well, which makes it interesting hiding place for rootkits. And every 8-byte entry in the GDT is a descriptor, and it could be a task state segment, a local descriptor table descriptor, LDT descriptor, or call gate descriptor, and I'll break these down. Task state segment, TSS, typically holds information about tasks and is used by the kernel for task management and scheduling. So it holds the processor's register state, I/O port permissions, stack pointers, and etc. relevant per process basis. And for the local descriptor table, it's going to hold memory segments that are marked private per each process, whereas the GDT typically contains global segments. Now, call gates are used for transferring control between x86 privilege levels on some old legacy systems, and this may typically it's not used on most modern systems. But it may have interesting implications as either a rootkit hiding place or some interesting hooking vector on some modern systems, but who knows. Next on the list is the SSDT, which is a system service descriptor table, and it's an internal dispatch table for scheduling. The IRP dispatch table for drivers, which is the IO request packet dispatch table. So when IO request packet comes to a driver, is going to look up in the dispatch table which function to call to handle that packet. So that's an interesting target for hooking. And so we've already covered the basics of hooking. However, in Windows, There are multiple challenges in the kernel, as there may be multiple copies of the GDT. The interrupt descriptor table and the MSRs on machine may differ, so having consistency across a rootkit on multiple platforms may be a great challenge. Um, so we're going to actually haven't covered all the basics to hooking. Let's get into it more once we cover the patching. I think it is the next slide. So again, to revisit the basics of hooking, you save the existing entry or contents in to the call table, swap in a new address for your hook. Maybe after you're done with at the end of your hook code, you return back to that call table or point it to the intended function. And this is useful for a number of things, for blocking antivirus checks or rootkit detection checks, for replacing the original routine, putting in backdoors, doing keylogging, looking for a specific password or username, credential entry, monitoring packets, and etc. Hiding connections and hiding in general from the user. So let's talk about countermeasures for hooking. Hooking can be easy to detect depending on how it's done. If it's for, say, the GDT or something like a driver IRP dispatch table, it can be easy to check for, because that should be static in that case, whether or not it's containing known good address ranges. This is similar again to the Linux kernel integrity measuring system approach. And many antivirus and rootkit detection techniques and tools do this. They look for simply sane address values in these various tables. So the way to get around this countermeasure is to either hook deeper or to do detour patching. So hooking deeper, all of the above hooking detection checks typically use the same system call to check the system call tables, which is ZW query system information. If you hook that, then you can lie to every application, tool, and antivirus check doing hooking checks. Alternatively, detour patching means leave the call table alone, and you patch the destination in the call table where there would be binary code, and just add a jump in there for the first instruction. Jump to your malicious code, and then either jump back or return back to the calling function. That brings us to patching methods for the fourth category of getting into the kernel. If you have system or admin privileges or the some equivalent privileges and have the ability to write into kernel space, you can do some patching methods. Now, what is called binary patching is modifying the binary on disk and waiting for a reboot. This is called a bootkit, and almost all bootkits are defeated today. Very easy to detect with any, trivial form or cheap or even free form of antivirus. Now, runtime patching is a bit more tricky. It requires modifying the memory image of a module or perhaps the kernel itself in raw memory. It's super hard to detect this. It's also super hard to do, but again, it allows high complexity and capabilities. So again, the ways to patch, say, a given function in memory is either detour patching or patching it in place. If your malicious routine is only so if the target function you want to patch, is only 10 bytes long, then you only have 10 bytes to do the malicious hook, which is quite limited in capabilities. So in-place patching doesn't offer as much capabilities as detour patching. At the end of the day, for an attacker, it's really hard to get into the kernel, so they really like to stay there and harden their access. They may go deeper into the BIOS or UEFI, or try to find ways, furthermore, try to find ways to otherwise retain access across reboots and even updates and patches to the operating system. This may involve patching the kernel, putting in some sort of patch into the boot process, and etc. So, to counteract this, because it was quite prevalent at a point, Microsoft introduced something called kernel patch guard, or rather, patch guard under kernel patch protection to protect against this technique. So, as the kernel operates, every now and then it will kick in and do integrity checks to make sure that the following EXEs and DLLs and kernel mode drivers are operating with good integrity. If the periodic check fails, the system will just die uh, or try to abort, probably boost screen of death. So the problem with this approach is there are two ways to get around it. Um, since it's a periodic check, if what you need to do in kernel space is quicker or really quick, you just drop in, do it, and then you restore the cable that you hooked or whatever you patched, etc., to whatever was the original code, and the integrity check would then pass. Alternatively, kernel mode drivers and PatchGuard as well operate at ring 0, so any rootkit can just stop in and tell PatchGuard, hey, I'm ring 0 also, why don't you just stop, okay? And it will comply. So Microsoft combats this with a crazy amount of obfuscation, which is perhaps the only way to do it since they uh, have everything relegated that level to the same permissions, and that is allowed. So finding the way to turn it off is what they've desired to make obfuscated. Now, for some theoretical countermeasures, in essence, both hooking and detour patching techniques modify constructs, either call tables or descriptor tables that are pretty static, or the text segments that contain the binary code, which almost should never be edited. So, in theory, it may be possible to safeguard kernels against those techniques by explicitly reconstructing them from known good versions, doing checksum based detection, and as well as doing direct binary comparison detection if that can be done. It depends on the kernel uh, boot process and how the memory space is all constructed, and whether or not there's any kernel ASLR going on. But this can be broken by modifying other kernel objects or essentially structures and objects that are destinations of the descriptor tables, as well as whatever the binary code is actually relying on to force it to perform malicious computations and etc. And this is just like Linux. Here there are very common targets: the eProcess object, which is targeted to hide processes; the driver selection object to load and hide a kernel mode driver. That should be KMD, sorry. Token objects, which are used for authentication, and so on. And it is probably impossible for a defender to exhaustively measure the integrity of all of these objects across all versions of an operating system, especially since they come out with a new one every 2 years. But I digress. Back in the day, about 15 years ago, honeypot operators used to release really interesting sessions when rootkits were really simple. You could read up on some of these sessions. They're at honeynet.org, and they're typically they used to do a honeypot session of the month or capture of the month. And on the left, this is a screen session grab of an attacker who managed to drop a shell on the target honeypot, and they're trying to manually install a rootkit on it and compile it. Pretty cute. But more relevant for today is a thing I'd like to leave for suggested reading. It is relevant to ARM and mobile, specifically targeting Android. It's the unexpected journey somewhat to Ring -2 rootkits targeting Trust Zone. Part 1 and Part 2 is listed here. And Trust Zone is very similar to Intel's System Management Module or Manager Module SMM, which is Ring -2 on the motherboard. And fascinating read. Highly recommend. And that is it for today's lecture. Thanks for watching.